Research is hard, but your tools should not be. Subthesis.com is the free alternative to expensive software. Whether you need to calculate Cronbach's alpha or organize your field notes, Subthesis has a tool for it. No paywalls and no registration required. Check the link in the description and let's dive into today's lesson. Welcome back to the PM Playbook. The critical path method, or CPM, sounds intimidating. It conjures images of complex network diagrams and mathematical calculations. Today I'm going to demystify CPM and show you why it's one of the most practical tools in project management. Here's the core insight of critical path analysis. Not all tasks equally impact your schedule. Some tasks have flexibility. If they slip a few days, the project still finishes on time. Other tasks have zero flexibility. If they slip at all, the project is delayed. The critical path is the longest sequence of dependent tasks. It determines the minimum possible project duration. By identifying this path, you know exactly where to focus your attention. Problems on the critical path are emergencies. Problems off the critical path might be manageable. Critical path analysis starts with understanding dependencies. Tasks in a project aren't independent. Some must finish before others can start. You can't test software that hasn't been developed. You can't train users on a system that hasn't been deployed. These dependencies create paths through the project, chains of tasks that must happen in sequence. When you map all dependencies, you'll find multiple paths from start to finish. The longest of these paths in terms of total duration is the critical path. Let's walk through how to build a network diagram and identify the critical path. We'll do this step by step, keeping the math simple and the concepts clear. Step 1 is to list all activities. Start with your WBS work packages. Each work package becomes an activity in the network. Add your duration estimates to each activity. Then identify immediate predecessors. For each activity, which other activities must complete before it can start? Create a table showing activity name, duration, and predecessors. This table is the foundation for everything that follows. Step 2 is to draw the network diagram. Each activity becomes a box or node. Arrows connect activities to their successors. Activities with no predecessors connect to a start node on the left. Activities with no successors connect to a finish node on the right. As you draw, multiple paths through the project become visible. You can trace from start to finish along different routes. The network makes the project's logic visible in a way that a task list cannot. Step 3 is the forward pass. This calculates the earliest each activity can start and finish. Start at the beginning of the network. The first activities can start at time 0. Add each activity's duration to find its early finish. For subsequent activities, the early start is the latest early finish among all predecessors. If an activity depends on 3 others finishing, it can't start until all 3 are done. Move through the entire network this way. The early finish of the final activity is the minimum project duration. Step 4 is the backward pass. This calculates the latest each activity can start and finish without delaying the project. Start at the end of the network. The late finish of the final activity equals its early finish. We want to finish on time. Subtract each activity's duration to find its late start. For predecessor activities, the late finish is the earliest late start among all successors. Move backward through the entire network. Now each activity has 4 values: early start, early finish, late start, and late finish. Step 5 is calculating float. Float, also called slack, is the amount of time an activity can slip without delaying the project. The formula is simple: float equals late start minus early start, or equivalently, late finish minus early finish. An activity with 5 days of float can slip 5 days without impacting the project finish date. An activity with 0 float cannot slip at all. Any delay becomes a project delay. Critical activities are those with 0 float. They form the critical path. Step 6 is identifying the critical path. Trace through all activities with 0 float. They form a continuous path from project start to project finish. Sometimes there are multiple critical paths. If 2 parallel sequences have the same duration and both have 0 float, both are critical. The total duration of the critical path equals the project duration. Any delay on the critical path directly delays the project. This is the path that demands your closest attention. Now that you've identified the critical path, let's discuss how to manage it effectively. The critical path isn't just an analysis exercise, it's a management tool. Critical activities deserve special attention. Track their progress more frequently than other activities. If you track most tasks weekly, track critical tasks daily. You want early warning of any potential delays. When problems arise on critical activities, escalate immediately. There's no buffer to absorb the delay. The project manager, the sponsor, and key stakeholders need to know right away. Remember, zero float means zero forgiveness. Every day lost on the critical path is a day added to the project. When you need to shorten the project, you crash the schedule. Crashing means adding resources to critical activities to reduce their duration. More developers, more testers, overtime, parallel work streams. Crashing always comes at additional cost, whether money, risk, or quality. Not all tasks can be crashed. Some have fixed durations, regardless of resources. To crash effectively, calculate the crash cost per day saved for each critical activity. Then crash the cheapest activities first until you've achieved the needed schedule reduction. Fast tracking is another technique for shortening the schedule. Instead of adding resources, you overlap activities that were planned sequentially. You start the successor activity before the predecessor is fully complete. For example, beginning development based on preliminary designs rather than waiting for final designs. Fast tracking increases risk. You might need to rework the successor if the predecessor changes. It requires careful analysis of dependencies, which really need to be sequential, which have soft dependencies that can be relaxed. Fast tracking is often faster than crashing but carries different risks. Float is a shared resource along a path. If activity A has 10 days of float and slips 10 days, all subsequent activities on that path now have zero float. They become critical. This means you shouldn't promise float to stakeholders. If you tell a team they have 2 weeks of flexibility and they use it, they may have eliminated the buffer you were counting on. Reserve float for unexpected problems. It's your safety margin against the inevitable surprises. The project manager should control how float is used, not individual activity owners. Don't focus exclusively on the critical path. Near critical paths, those with small float, deserve attention too. A path with only 3 days of float can become critical with a small slip. Monitor near critical paths alongside the critical path. When problems arise on near critical activities, they might not be emergencies yet, but they're close. If your project has multiple near critical paths, your overall schedule risk is higher. The more paths that are close to critical, the more likely it is that something will cause a delay. The critical path isn't fixed. It can change as the project progresses. If a critical activity finishes early, a near critical path might become critical. If a non-critical activity is severely delayed, it might become the new critical path. What was critical yesterday may have float today. What had float yesterday may be critical today. Reassess the critical path regularly as actual progress is recorded. Your scheduling tool should recalculate automatically when you update task progress. Review the results. You don't need to do these calculations by hand. Scheduling software like Microsoft Project, Primavera, and many others perform critical path analysis automatically. Enter your tasks, durations, and dependencies. The software calculates early start, late start, float, and identifies the critical path. Update progress, and it recalculates. Your job is to ensure the logic is correct and to manage based on the results, not to do arithmetic. Understand the concepts so you can interpret what the software tells you. Watch for common mistakes. Missing dependencies create false float. If you forget that testing depends on development, your schedule will show float that doesn't exist. Wrong durations distort the critical path. Over-optimistic estimates might misidentify what's critical. Ignoring resource constraints is a big one. Critical path assumes unlimited resources. In reality, the same person might be on multiple tasks, creating hidden dependencies. And treating the plan as reality rather than a model. The schedule is your best guess. Reality will differ. Standard critical path analysis assumes unlimited resources. Every task can proceed as soon as its predecessors are complete. In reality, resources are constrained. You might have only one database administrator. If two tasks need the DBA simultaneously, one must wait. Resource leveling adjusts the schedule for actual availability. When you level resources, the schedule often gets longer, and the critical path may change. What was parallel becomes sequential due to resource constraints. Always level your schedule before publishing dates. Let's practice. Think of a simple project you know well, perhaps with 5 to 7 tasks. Sketch the dependencies between them. Draw arrows showing what must complete before what can start. Which path through the project looks longest? That's likely your critical path. Where would delays hurt most? Tasks on that longest path are where problems become project delays. This quick sketch can reveal insights even without formal calculation. Let's summarize. The critical path is the longest sequence of dependent tasks through your project. It determines minimum project duration. Critical tasks have zero float. Any delay directly impacts the finish date. When you need to shorten the schedule, crash by adding resources or fast track by overlapping activities. Both have costs and risks. The critical path can change as the project progresses. Monitor it continuously and reassess when actuals differ from the plan. In our next lecture, we'll complete Module 2 with risk management. You'll learn how to identify risks before they become problems and how to create response strategies that actually work. A risk register is only valuable if you use it, and I'll show you how. Thank you for working through critical path analysis with me. It's one of the most powerful tools for schedule management. Now you know where to focus your attention. I'll see you in the next lecture where we tackle risk. Research is hard, but your tools should not be. Subthesis.com is the free alternative to expensive software. Whether you need to calculate Chromebox Alpha or organize your field notes, Subthesis has a tool for it. No paywalls and no registration required. Check the link in the description and let's dive into today's lesson.